Greetings. This is a modified version of my 2016 APS March Meeting talk. This work was done with Mark Matson, and relevant links are in the description. Without further ado, I present Monte Carlo Field-Theoretic simulations of a homopolymer blend. This work examines the equilibrium behavior of binary blends of A and B homopolymers, labeled here in red and blue. The mean field phase diagram is shown here in terms of the interaction strength given by the Flory-Huggins interaction parameter chi-n on the vertical axis, and the volume fraction of A homopolymers, phi A, on the horizontal axis. At low interaction strength, equivalent to high temperature, the polymers mix together. At higher interaction strength or lower temperature, they phase segregate into an A-rich region and another B-rich region. The mean field picture from which this phase diagram is derived assumes that the system only adopts one single most likely configuration and ignores fluctuations about this configuration. The mean field picture is only strictly correct when polymers are infinitely long. Although it does a good job for long and strongly stretched polymers, it fails close to the order-disorder transition. Our use of field-theoretic simulations allows us to go beyond this mean field calculation to find fluctuation corrections that come about due to the finite size of polymers. In what follows, we start by examining the structure function in the mixed state of symmetric blends. We then move on to locate the phase transition, that is, we find the value of chi-n where the mixture phase segregates. But first, I want to describe how field-theoretic simulations work. Mini-simulations, unlike ours, are particle-based, meaning that they represent each individual particle or each individual polymer. This makes them extremely computationally intensive. In our work, we start by representing polymers as Gaussian chains, that is, we think of them as thin elastic threads. The partition function of a blend of Gaussian chains can be written in terms of an integral over all possible configurations of the polymers. This is represented here by the functional integral over paths R of S, summed over all chains indexed by alpha. In this equation, U represents the interaction energy between A and B monomers, and the stretching energy is included in P. Actually performing this integral is extremely difficult to say the least, so instead we perform an exact mathematical transformation from a particle-based representation to a field-based representation. After the transformation, the partition function is given by an integral of the effective Hamiltonian over the fields. These fields, W- and W+, are respectively a composition field that couples to the difference in A and B monomer concentration, and a pressure field that couples to the total monomer concentration. When performing these simulations, the fields are represented on discrete grids as illustrated. The discretization can be represented equivalently as either a grid size delta or, in Fourier space, a wave vector cutoff lambda. The reason for bringing this up will become clear shortly. Once we have this field-theoretic model, there are two common approaches we can take. We can simplify the problem greatly by going with mean field theory. This involves doing a saddle point approximation to the integrals over the fields, thus avoiding all the difficult integrals. This essentially approximates the system by its single most likely configuration. This approach, known as self-consistent field theory, has been shown to be extremely useful. There are other, less approximate ways of approximating the integrals. One can, for example, expand the exponential to Gaussian order, adding a fluctuation correction to mean field theory. Another notable example is renormalized one-loop theory, which expands the integral into a set of integrals given by Feynman diagrams and, as the name suggests, expands up to one loop. We use a numerical approach to evaluate the integrals, field-theoretic simulations. Specifically, this work uses Monte Carlo field-theoretic simulations, which involve using Monte Carlo to sample the composition field. We still employ the mean field approximation to the pressure field. This turns out to be a good approximation for our system. There are also technical reasons why it's difficult to use Monte Carlo to sample the pressure field. The pressure field can be sampled using complex Langevin simulations, but the relative merits of different types of field-theoretic simulations are beyond the scope of this talk. Let's take a look back at these discrete grids on which we represent the fields. These fields are continuous objects being approximated for numerical purposes on a discrete grid. For both self-consistent field theory and field-theoretic simulations, we would therefore expect that as the fields are more precisely represented, that is, for a smaller delta or a larger lambda, the calculations would become more precise and should converge to a single solution. This is, however, not the case. To see why, let's take a look at how the free energy depends on discretization. We can expand the free energy of the disordered phase. The first term corresponds to uniformly mixed state. The second term depends on the structure function S and the composition fluctuation. The structure function varies approximately as k squared, where k is the wave vector, so its inverse varies as 1 over k squared. The overall contribution of this term to the free energy therefore varies as the k volume integral of 1 over k squared, which can be written like this. Note that there's some wave vector cutoff imposed by the simulations as previously described. Evaluating this integral, we see that the result is proportional to the wave vector cutoff, lambda. The free energy thus increases with increasing lambda and diverges as the wave vector cutoff diverges. That is, as the lattice spacing tends to 0, or as we continuously represent the fields, the free energy diverges. It turns out that we can absorb this diverging part of the free energy into the part of the free energy that represents the AB monomer interactions. You'll have to see Olivera de la Cruz 1991 for details, but the result is a renormalized interaction parameter, chi effective. The renormalization factor depends on the wave vector cutoff, lambda, as well as the invariant polymerization index, n bar. The factor becomes more significant for finer resolutions and also for shorter polymers. Now that we have all that out of the way, we can move on to some results. We start by looking at the structure function for very long polymers, n bar of 10 to the 5, just below the order-disorder transition, that is, when they're mixed, but almost want to phase segregate. The solid curve is the RPA, or mean field structure function, and the points and colored curves come from simulations. The mean field, or RPA, structure function is calculated at chi-n of 1.9, and all the simulations are done at a bare, not renormalized, chi-n of 1.9. Different sets of data correspond to different resolutions. For the most part, the data overlap, but you'll notice that the finest resolution deviates a little from the others. When we change to looking at simulations conducted at all the same effective chi, the overlap improves and they all agree quite well both with each other and with RPA. Moving to shorter chains, n bar of 10 to the 4, the difference is a bit more obvious. That is, there's less overlap between different datasets. Once again, looking at the structure functions calculated at the same effective chi, the difference essentially vanishes and the curves collapse onto one another. Moving to even shorter chains, close to what's actually used in experiments, n bar of 10 to the 3, the difference between these curves becomes quite striking. It's evident that if you're doing similar simulations at different resolutions and not accounting for this UV divergence, the results can't be meaningfully compared because the resolution itself makes a significant difference. Taking the UV divergence into account, however, by renormalizing the interaction parameter, removes this barrier and allows simulations done at different resolutions to be meaningfully compared. Our next step is to locate the macrophase segregation transition. This transition occurs at a critical point where finite size effects are very important. In order to get around this problem, we use finite-size scaling. In particular, we use the fourth-order cumulant method. This method involves calculating moments in the difference in the average instantaneous A and B monomer concentration, that is, moments of the average composition. These moments are labeled UL. We want to obtain cumulants UL as functions of chi-n at different system sizes. Rather than doing a whole lot of simulations at different values of chi-n, we use a reweighting technique that allows us to calculate a curve UL as a function of chi-n from a single simulation conducted close to the critical point. We do this simulation and then reweight the statistics of the result to get the entire curve. Plotting UL versus chi-n turns out to be extremely useful. This is because it has 3 fixed points. At high chi-n it tends towards 2/3. At low chi-n it tends towards 0. In between there's a third fixed point at the critical point. These fixed points don't depend on system size. This isn't too useful for the high and low fixed points, however the one at the critical point becomes quite useful. This is because it allows us to conduct simulations at different system sizes, calculating a curve for each system size, and look for where the curves overlap. This gives us a very precise location of the critical point. In mean field theory, the critical point is exactly at chi-n equals 2. Comparing this to our result, we see that it's shifted to a higher chi-n. This indicates that fluctuations suppress the phase segregation of A and B polymers. This is consistent with fluctuation effects seen in other polymer models. Earlier I mentioned the approximate analytical renormalized one-loop theory. ROL also predicts a suppression of the transition, but it indicates that fluctuation effects are stronger than we've found using field-theoretic simulations. We have once again started with very large polymers, n bar of 10 to the 5. These polymers are quite large compared to those used in experiments. As we move to shorter polymers, n bar of 10 to the 4, we see qualitatively the same behavior. The transition is suppressed, moved to higher chi-n. However, for these shorter polymers, the transition is more suppressed. For even shorter polymers, n bar of 10 to the 3, once again we see similar results. Combining these data and plotting the location of the critical point as a function of chi-n, for the larger polymers we see a similar trend to that seen in ROL, however the transition is not as suppressed as we predicted. As we move to an n-bar of 10 to the 3, we see that the trend is not monotonic, and the transition actually goes down as compared with 10 to the 4. In this work, we studied the equilibrium behavior of a binary blend of A and B homopolymers using Monte Carlo field-theoretic simulations. The results that we found depended significantly on the resolution at which the simulations were conducted due to a UV divergence. Correcting for this UV divergence by renormalizing the interaction parameter reduced the discrepancy and allowed for meaningful comparisons between simulations done at different resolutions. Monte Carlo field-theoretic simulations allowed us to evaluate the effective fluctuations on the critical point in these binary blends, and we found similar results to those found in ROL, especially for the larger polymers. This brings me to the end of my APS talk. If you found it interesting, check out the links in the description. You might also enjoy my work on microemulsions in ternary blends. Thanks for listening.